Hello, hello everyone.
Yes, we can see the presentation and hear your voice.
Okay. Yeah. Okay.
Let's start.
Thank you, Professor Han. And my name is Ziwei Chen, and I'm a research fellow in Building Energy and Environment Research Group at University of Nottingham. I'm glad to be here to briefly introduce our recent project called Innovate Composite Smart Materials for Heating, Cooling, and Humidity Control in Buildings. And for our project, we called the THEMAC in short for Total Heat Energy and Moist Air Control. And this project is a 36-month industry research project funded by Innovate UK. And we, University of Nottingham, as the academic institution, worked with 4 industry partners. 3 of them are based in the UK. One is the phase change material manufacturer, and one is the heat pump manufacturer, and one is the building construction company. And we have a voluntary partner from France for providing the phase change material to us. So the main project aim is to develop a total comfort solution by controlling both indoor temperature and humidity. So the THEMAC will passively respond to occupancy and daily or seasonal changes. Although the THEMAC system was developed prior to the pandemic in 2018, it still offers great feasibility for building applications to address the indoor environment for the post-pandemic living. So to begin with, the THEMAC system, this schematic diagram illustrates the system component and how it integrates. So we have 3 main components in the THEMAC system. We have the phase change material, PCM-based cylinder to handle the passive cooling, and we have the solar assistant heat pump to provide heating, including the hot water supply and the space heating. And we have the super absorbent box containing the composite material to handle the dehumidification, and part of the heat generated by the solar assistant heat pump will be used to regenerate the absorbent. So for the working principle of the THEMAC system, it's quite straightforward. So it will be able to operate throughout the year. In summer, during the daytime when the ambient temperature is high, the warm air in the building is circulated through the PCM panels. Hence, the heat from the indoor environment will be absorbed by the PCM cylinders as the PCM melt. In such a way, the PCM will enhance the overall thermal comfort in the occupied space by maintaining a steady indoor temperature within the comfort zone for longer periods, thus to minimize the time depending on the HVAC system and prevent the overheating during the daytime, especially on hot days. On the other hand, the absorbent will control the air humidity level of the building when dehumidification is desired. And throughout the day, the PCM will fully absorb the heat from the building. So in order to allow the PCM work for the following days, at nighttime when the ambient temperature drops, the fresh, cool air will from the outside will be circulated into these PCM panels, causing them to freeze and to release the stored heat from the daytime. Therefore, the PCM panels will become ready to begin the next cycle of absorbing the heat again. And then for the winter operation, when the heating is required, the heat pump will extract the heat from the outside and the solar energy to warm the building, and the excessive heat generated by the heat pump will be stored by the PCM panels and will be used when it's needed. So we firstly conducted the research on the PCM material selection because the 3 key properties for any potential phase change materials includes the suitable melting temperature, desirable heat of fusion and thermal conductivity, one of the key property governing the initial selection is the melting temperature for the PCM. So as stated in the literature, the suggested room temperature in winter would be 23.5 to 25.5 Celsius, and in winter it will be 21 to 23 Celsius. So as suggested by a lot of literature and research, the preferable phase change material melting point should be 1 Celsius to 3 Celsius higher than the average room temperature. So we consider the melting range of the phase change material would be 18 to 29 Celsius. And this chart shows the market available PCM materials with the melting temperature in the range of 0 to 35 degrees. And because we have two phase change material manufactured in our project team, so we select the material from their category. So we choose 3 different types of the PCMs for the THEMAX system, including the salt hydrate one and the paraffin-based organic PCM, and then the bio-based micro-encapsulated PCM, all with a melting temperature in the range of 23 to 28 degrees. So in terms of the PCM integration to the built environment, encapsulation is the common method. So we proposed and tested a lot of different designs to accommodate the PCM depending on their types. For example, we use the aluminum honeycomb structure to accommodate the organic phase change material and the micro-encapsulated PCM. And because of the salt hydrate PCM is corrosive to the metal material, so we use plastic pouches to accommodate. And we also have a painted design called blister structure. So it's similar to a medicine pill structure, but we filled the cells with the micro-encapsulated PCM, and then to create a panel as seen in the photos. And the advantage of the blister panels are lightweighted and with a more heat transfer surface areas, and it allows flexible design and integrate to the ceiling. And based on our testing, the blister panels did work to passively respond to the room temperature. And based on that blister design, we have finalized the final product design called Thin Ice, worked with our industry partners, and here's the photo showing the overall view of the panel. So we use the HDPE module to accommodate the PCM, and then we integrate several heat transfer enhancement materials to improve the thermal conductivity of the HDPE module. And then we have designed the design with more surface areas, and it allowed the panel to be stackable into multiple layers, and 1 square meter would allow 8 modules. So we have done several field testing using the Thin Ice panels. For example, there's one testing, we use a small storage room and we place 14 Thin Ice panels on the ceiling level to cover 25% of the ceiling area. And as we can see from the result chart, the room temperature would be stable and maintained at around 27 Celsius. And in terms of the practical application of the Thin Ice panels, we can also apply their profited metal panels, like on the right-hand side, to provide a better finish and better looking within the room. And for the solar assistant heat pump, in our field testing, we aim to provide hot water supply and coped with end-of-flow heating pipes and the thin-line PCM panels. So during our field testing in winter days, the heat pump was able to maintain a high temperature hot water delivery above 60 Celsius for a period of 8 to 10 hours during the sun hours, and the energy would be stored in the thin-line panels, and the space heating temperature during the daytime would taking up to 32 degrees, which showed a temperature differential of 28 to 30 degrees between the indoor and outdoor temperature. And at night, the stored heat from the thin-line panel will be released for the space heating, and the result shows that the indoor temperature of around 22 Celsius would be achieved during 12 hours. One of the other functions for the heat pump is to provide a heat source to regenerate the absorbent box. So we designed a super absorbent box as shown in the photo. So the box encloses the solid desiccant across 4 levels to maximize the air distribution. The desiccant we choose is the vermiculite combined with magnesium sulfate and calcium chloride. The selection was chosen based on the research by other research projects in our research group. And then we integrate the hot water pipes throughout all the levels of the panels to allow the hot water generated by the heat pump to flow across all the material for regeneration. And during the test period.
Excuse me, Doctor.
Yep.
Yes, I appreciate if you speed up. Yeah, your presentation.
Okay.
Thank you. Yes.
Yeah, and then based on the testing data, the superabsorbent would be practically absorb the moisture from the indoor environment, and the hot water generated from the heat pump could reach up to 85 degrees, which is sufficient to regenerate the vermiculite composite desiccant. And due to the pandemic, it's a pity that we haven't got enough time and opportunity to do the full year testing to cover all the seasons to test the integrated THMAC system. But this industry research provide the proof of contact of the THMAC technology. And here is the overview of the published work we have done during the project, including the journal papers and the articles which is public, and to promote the THMAC product. And that is all for my presentation. Thanks so much.